Absolutely. Fundamental theorem. So looking at this setup, okay, like I'm stating that this is a fundamental theorem question. Like this is related to that second part of somehow taking the derivative of an integral actually. Now if you're just kind of looking at this, aren't I going to need to integrate 2 sine of x at some point because I need to find the antiderivative? In other words, because I need the derivative to be that. So I'm going to need the antiderivative of 2 sine of x. So I hope you probably thought about that. How many of you started right there and just said, I need the antiderivative? Okay, so what is the antiderivative of 2 sine of x? Keep going. Plus a constant. So there's really our antiderivative. That's where we could have jumped right into this question to write something down. Because the derivative of that is the 2 sine of x that I'm stating. Well, why is this y of pi equals 3 even given then? So you can find the constant. So if you substitute in pi, what's cosine of pi? -1. Cosine pi over here. Cosine of pi, left, x, -1. What's c? C would be 1. So the final answer here is this. Y equals -2 cosine of x plus 1. Now, what I'm wanting to show you is another way we can think about this, because if you clicked the help me solve it in my math lab, they were setting up an integral for some reason. And I want us to kind of walk through that and why sometimes we're going to have to do that. So, what if I first just started to write something like this? The integral from, I don't know what that lower limit is right now. I'm going to put an a. I'm going to put an x here. And I'm going to copy this function here, except I'm going to use a different variable. This is what we were seeing the other day, right? This is actually what we saw yesterday, that if we don't have different variables there, it could get really confusing. So my first thought is that if I take the derivative of this, right? So if I call this y right now, and I take the derivative of both sides, what is the derivative of this integral that I've written? A is a number. I just don't know what it is right now. What is the derivative of the integral from a to x? A is a number, x is a variable, 2 sine t dt. 2 sine x, right? The original function back here, right? That's the work we've been doing. So that means that right now, that function is a good start to our final answer then, isn't it? Like it has the right derivative. So in other words, it is the antiderivative. Now there's this a that I don't know, but a is probably related then to the c that I don't know, right? Going back over here. So let's look at this then from a perspective of maybe substitution. Now if I put, can I erase this part here? Are we good with that? Like that's just kind of a perspective there. So how about this? There should be some constant that I'm going to need to include. Okay? Now, it seems like there's too many things we don't know maybe at first. Right? I don't have a lower limit, and I don't really know what this constant is that's going to make me get the right answer. Remember that this piece really should be the antiderivative of the upper limit minus antiderivative of the lower limit, right? So I'm going to write something here, and I want you to talk about why this is going to be the same answer that we just did. Okay? So here's what I'm going to say. Thinking about this and thinking about this constant, these two pieces, if this lower limit is equal to that x value, this constant should be equal to that y value. So I'm saying that y should be equal to the integral of from pi to x of 2 sine t dt, write that dt, or I'll mark it wrong because I can't tell where this 3 is. Why does this give the identical answer of this? Talk that through at your table. Talk that through. Why does that integral give the same result? Why are these the same? Okay. Okay. Wait, are you saying because this is really f of pi? I'm sorry. I pushed that up. That this is really f of pi? So if I write this out, I would have something that looks like that. I was liking where you're going, but now I'm confused to what you're saying. Oh, so right here, like when you're substituting in, so you're really thinking about putting a pi in here for x, is that what you're saying? So if I put a pi in there for x, let me rewrite this. I thought you were describing it a little different than you maybe were. If this is pi, what is that? It's 0, right? There is no region then. So what is y equal to? 3. Do you see that thinking of this as a function, if these limits agree, there's that shift. If I take the derivative of this, do I get what I'm expecting? Well, this would be, again, if I would write it out and say, okay, so if I'm wanting y prime, I need to take the derivative of this whole side. Okay, I need the antiderivative of the upper limit minus antiderivative of the lower limit. And I thought this is where you're first going, Nene, but this, do you notice that these pieces here are canceling each other back out? That if 3 really is capital F of pi, I'm subtracting f of pi, capital F of pi, and then I'm adding capital F of pi. And then, well, shouldn't the derivative of this antiderivative take us back to where we started? Even if there's a constant here that I don't understand, right? Like that shift doesn't matter when I'm going back the other direction. And it really wouldn't even matter anyway, because these are all constants. Here's what this means. If you take your calculator for me, grab your calculator, and in y1, here's what I want you to put. Now, I'm not going to have you graph this because I think you should know what that looks like. This, because we're really saying these two functions are the same function. That's what we're saying. So we should think that this graph should be a cosine curve with an amplitude adjustment flipped over and then this shift of 1, right? It's those pieces all combined together. So that's what I should see if I type this into my y equals menu. So if we type this in, and that's what I want you to put in, and this is going to graph pretty slow, so choose the integral from the calc menu, put the function in, just put that exact thing in. Lower limit, upper limit's x. Be sure the 3 is outside the integral because that's what we're saying. And if you hit graph, you should start to see this graph be constructed. On the 84, you have to use x's in every spot, though we just said that that's not a good idea because it gets confusing, but your calculator doesn't understand it any way else. We're going to talk about it. Okay, I'll try to fix it in a second. Okay, so first, hopefully you're seeing the cosine curve that we just described, right? It's going to be a little slow. So here's the point again. This circled thing is the same as this circled thing. They're just different representations of the function. Now, if you're wondering, like, why this one has a +1 and this one has a +3, don't forget that there's actually another constant involved in what we wrote here, right? So if we think about the antiderivative, like just this, if I'm not taking the derivative of it like here that I've written, if I would just say, what does y equal? Well, it should be the antiderivative evaluated at x minus the antiderivative evaluated at pi plus 3. These pieces right here should be combining together to get this. Okay. You can check that if you want. So, new problem. And here is why we have a need for writing it as an integral. Like in that last problem, it's actually way easier to sit there and go, okay, what's the antiderivative? Put a plus c, solve for c, done. Okay? Except the trouble here is, do we know the antiderivative of the sine of x squared? We know it. Like you might first start making a guess that, okay, should be maybe like a negative cosine of x squared, right? That's what I would expect. Maybe the derivative of cosine is negative sine, put a negative there to fix it. Except this x squared is going to cause a lot of issues. Why? Chain rule. Okay, so the chain rule would multiply that by 2x when I would take the derivative. So sometimes people think, well, what if I just divided this by 2x so the 2x's cancel? Except, how do you take the derivative of this now? Quotient rule. That's not this. Right? Do you see that we really can't fix this the way that we have been doing questions, which means if I want to know what y equals, really the only way that we can do that is to write some integral. So what you need to write is some integral here plus some constant such that y of 0 is 4 and the derivative of what you write is the sine of x squared. If you can do those two things, you've got the right answer. Try it. It should take you 30 seconds. You done? You should be. Here's the answer. If you have an x in the wrong space, it's also wrong. Careful with x's and t's. Ethan. Are you asking if this was x squared instead of t squared? If you would do that, so this is a good question related to what we've been working on. If you put an x squared here and you put a t here, like the first part of it's going to kind of look right because you're going to substitute an x squared in for t, but don't forget you'd have a chain rule for this, which means there would really be a 2x here that we don't have. So that's how we know that's not the case, that it's really got to just be that. Yeah, it's the limits. And if you work out all the steps, you'll see that, well, whatever this antiderivative is, even though I don't know what it is, its antiderivative should deal with that chain rule, that x squared piece, right? That's where that piece should already be taken care of. So here's an interesting thing. You ready? And then I'm done. We don't know this antiderivative, right? You just told me we didn't know how to write it. Do you realize we can see a graph of the function that we can't write? Isn't that interesting? I can put this into my calculator, and I can see the graph of the function that I don't have this better form for to recognize what it is, which is a really curious thing of how we can use this fundamental theorem. Okay, so here's the really powerful thing, and then I'll take any homework questions. When you think about the usefulness, think about what this is. Now in BC, we're going to do something called Euler's method, which is related to this thought right here. We're going to do an activity, and there's a, have you seen the movie Hidden Figures about the women in NASA, right? There's a moment in that movie where one of the women is describing using Euler's method, trying to find the trajectory of the path. You have a vague memory of something like that. She says we got to use something old to find this answer, and it's related to this thought that if I know a rate, because they knew the rate, they know the derivative, but we actually don't have a very nice function to describe it, right? If they had the function to describe the path, then there's no problem. But we don't know the path, but we have the rate. And we have a moment, we have a point that we know it has to go through. That's the reentry point. Then I could write something about a function just knowing the derivative and have a computer start calculating positions, which is related to what you saw in that little clip in the movie. So that's just a neat connection as to why we might not have the function, but we could learn things about it. We're going to talk about how Euler's method is actually the full extent of what was being expressed in that movie in BC, and we'll do an activity involving it. Okay. So I think that is all I have for you. Definitely some of these questions possible on the test. Again, it's really, to me, fundamental theorem backwards, because if I started here and said take the derivative, you'd write this. You should be able to tell me it goes to that point, so it's really that same thought, just kind of backwards. Anything you want to ask me from homework now? Now would be a good time to do that. Homework questions. Yeah, Siri, what do you have? Like on what it's trying to show?
Yeah, like how to decide.
I kind of saw it, but...
Okay, it's gonna take 5 minutes, but it was like that. Oh yeah, okay, so So you have to find that shading when not on the board.
Okay, yeah, well, let's talk about that. So, what number was this, Siri? So in 20, it's asking for some shaded region that's not to the x-axis. And they give you these functions, though, here and here. So really what we want to do is maybe think about how we could think of two areas or two integrals that might give our answer. Sadvika, did you have a thought? You're agreeing to that. That's a good strategy. So the box, I assume, is like, because this was a horizontal line, I think, in the problem, wasn't it? So you're saying find that whole area, subtract the integral, leaves you with the black region, right? So it's just matching what you know and manipulating it to get it. So you could try to write a single integral to get that answer. We'll do that in chapter 7. This is way simpler. I would even do this even if we knew another method. What else you got for me? Other homework questions? Yeah. Sure. Oh, I forgot to tell you this. I remembered this morning. So Simpson's rule, strike that. So you can delete all the Simpson's rule questions. We don't need to do that. It's another approximation method. I'll tell you what it is, and you'll realize, maybe you'll have appreciation for the fact that when I was in calculus, we had to solve for all of these by hand. But if we would have points, and so trapezoids are easy, right? We can make trapezoids. We can find on some area. What Simpson's rule says is this. Well, if I know that from here to here is a curve and not a line, why don't I construct some parabola between those points and find the area under that parabola for that little region? And so you have to construct different parabolas on every section. Yeah, that's super annoying. At that moment, why don't we just find the function or use a trapezoid, like more trapezoids, right? So I'm not going to ask any questions about Simpson's rule. That actually deletes quite a few homework questions there. Apologies for keeping that on there. Sure. And we are taking the derivative of that. Okay. Yes? What you got? Okay, so what if that was like a 1? Tell me what you would do then. And you're done? If this is a 1, are you done? Yeah, you are. Because you would have the antiderivative. So if I'd try to write this out in some extra symbols here, like it'd be antiderivative of x cubed minus the antiderivative of 1. You have given us the right derivative for that first part. What's the derivative of the second part? That's 0. We don't need to worry about it. Done, right? So if we know that, though, like this has to then be part of the answer, right? So here's the only difference. If I would then just go back to this work and I change this to x squared, that piece just isn't 0 anymore. So what could I write here to finish the problem if this is an x squared? Cosine 2x squared times, and how do I connect these together? Yeah, because this is subtraction, right? So we're subtracting those pieces, so there it is. So it's really just an extension of what you were already doing. It looks different, but it's really just because this piece doesn't drop out, we do the same process we did with the first one. Don't forget it's just upper limit minus lower limit, so that's where the minus there is coming from. Okay. What else do you want to ask about? Chrissy, that's the chain rule right there. Chain rule right there. Remember, this is the inside, right? So those insides are where those chain rules are coming from. So it's really the limits. I think, Brian, that's what you were saying earlier. It's the limits that are producing the chain rule, not this piece in here. Because in here, that would be wrapped up in this capital F, whatever capital F is. It's already would have been taken care of. What else you want to ask me? Yep. Yep. Okay. Is it f of t dt? Okay. Okay. So these questions, and there's another one that's kind of like these that says something like it gives an integral of some function, and it says like over here 3x plus 6, or it gives you some value. All of these are kind of in the same class for me. Some of you aren't paying any attention, which is unfortunate. So all of these are kind of in the same class of questions for me. Like they're best solved by probably writing in different symbols than they're given. So like for the one that you're asking about, like I would just say, okay, can I write, like do we know A and B? I think we do. A is -1, B is 2, and I think we know the function. I wrote t's, but did I write the right function? Okay, so I would say let's try to write in symbols what this side is really saying. So we need to find the antiderivative of this function. We would substitute in the upper limit, which is x, minus that antiderivative, substitute in -1. I'm not actually going to work at this right now, but I'm just going to say I could find that antiderivative, not difficult. I could put an x in there if I wanted to. There's going to be a plus c. I don't care about that. You'll see why. Over here, so there's still this plus k. This side, do the same thing. It's the same antiderivative, right? Same function here. So it's the antiderivative value at the upper limit minus antiderivative evaluated at the lower limit. What do you notice? Those are gone. So with what I'm left with, well, if I could find an antiderivative for this, so what would capital F of t be? I'm going to need that now. So can you look right there and tell me super fast? One-third t cubed minus what? 3/2 t squared plus c. Okay. So careful with this negative here. This is still being subtracted. Okay, so now substitute in -1 to that. Write that answer plus k. You have this negative here. Substitute in 2 to that. Do you notice that the c's are going to cancel out here again? Right, you're going to get a plus c on both sides. And do you notice then the only thing that you really don't know is k? It's just a rearrangement from there. So if you don't get that, it's arithmetic maybe mistake. Just try it again. But that should be, like, careful with that negative sign. That might be an easy one to drop in the middle here. But that's the structure of solving one like this. So I think it's helpful to kind of write it out. Like, what is that really telling me? When you see it in different symbols, you go, oh, wait, there's a part of this that is not in the problem anymore. Okay, I'm going to stop here. You've got 10 minutes. So today, you can work on whatever you still need to work on, anything from section 5. I think there's a review for my math lab. I'll have for you tomorrow for the weekend to have some like 30 additional paper questions that you can take with you and kind of work on, and we'll finish those on Monday and talk about any questions you have. Test Tuesday. That's what I've got. It very well could be a take-home quiz. We'll see.